There are three problems in hidden Markov models. With problem 1, given the observation sequence O with time 1, we have O1, with time 2, we have O2, and up to OT, and a model. And we know the parameters A, B, and P. How to efficiently compute the probability of the observation sequence P of O given lambda, and lambda is the model. Problem 2 is given the observation sequence O and a model lambda, how to select a corresponding state sequence Q, which best explains the observations. And problem 3 is given the observation sequence O, how to adjust the model parameters A, B, and P to maximize the probability P of O given lambda. So first, let's talk about the problem 1. Problem 1 is also called the evaluation problem. Given the observation sequence O and a model with parameters A, B, and P, how to efficiently compute P of O given lambda. So let's look at the solution. For state sequence Q, from Q1, Q2 up to Qt, the probability P of O given Q and lambda is the probability of observing O1 at state Q1 times the probability of observing O2 at state Q2, and etc. up to time t. And the probability of a state sequence Q, P of Q given the model, is the probability of arriving at state Q1 times the transition probability from Q1 to Q2 times the transition probability from Q2 to Q3, etc. up to Qt at time t. So the joint probability P of O and Q given lambda is the conditional probability of O given Q and lambda times the probability of Q given lambda. Then we sum for all the possible state sequence. To get the probability of O given lambda. And this is what we have. So basically it is the sum for all Q of the probability of arriving at Q1 times the product for all time t from T2 up to T of the transition probability from Qt minus 1 to Qt, and times another product from T of 1 up to T, capital T, of the emission probability of observing OQT at state QT. The problem is the number of calculations is high. Let's look at the algorithms, namely forward and backward algorithms. In the forward algorithms, we define a forward variable alpha ti, which is the probability of partial observation sequence up to time t with state si at time t. So in step 1, for initialization, alpha ti is set to the probability of arriving at state I times the emission probability of observing O1 at state I. And then in step 2, this is induction step, we calculate alpha t plus 1 j. So alpha t plus 1 j basically is based on all the alphas in the previous step. It is a sum of alpha ti, which is in the previous time, times the transition probability of transiting from state I to state j, and we sum for all I from 1 to n. And this is illustrated here. Then at the end, we have the probability of O given lambda, which is the sum of alpha ti for all I from 1 to n. Now let's look at this example. How to calculate P of O given lambda. And this table provides the initial state properties P. The probability of arriving at state S1 is 0.2, at S2 is 0.5, and at S3 is 0.3. And also, we can see the transition properties between states. For example, from state 1 to state 3, it is 0.5. From state S2 to S1, it is 0.4. Also, we can see the emission properties. For example, at S1, observing X1, it is 0.4. At S1 and observing X2, it is 0.6, etc. So assume that we observed at time 1 and time 2, we observed X2 and X3. So following the formulas, we can compute the forward probability alpha 11, alpha 12, and alpha 13. They are all at time 1 for 3 states, S1, 2, and 3. And they are correspondingly equal to this. Basically, it is probability of arriving at S1 times the probability at S1 observing O1. And replacing the numbers in, you have this. Similarly, for the second, this is the probability of arriving at state S2 times the probability of being at S2 observing O1. And it is 0.2 times 0.5 and is equal to 0.1. And similarly, for the last one, you get this, and it is 0.21. Then we compute the forward properties for time 2, alpha 2, 1, alpha 2, 2, and alpha 2, 3. So following the formulas, we get the probability which is 0 for the first, 0.4096 for the second, and 0 for the last. And then putting all the numbers in the sum from 1 to n for all the states at time t, time capital T, which is time 2, we get this. And this is the probability of the sequence O given the model lambda. And this slides illustrate the computation of the forward probabilities in a trellis. And you can see on one axis we have states from 1 to n, and the other axis we have time from 1 to t. Let's move on to the backward algorithms. We define a backward variable beta t of I as the probability of the partial observation sequence after time t given the states Si at time t. So this partial observation starts at time t plus 1 up to time capital T. In step 1 for initialization, beta Ti is set to 1. And then we compute backward. The computation for beta is illustrated here. From beta t plus 1, j, we compute beta t I. And finally, we can get the probability of the observation sequence given the model, which is the sum for all the states of pi times beta ti.